Jensen's inequality is a tiny sentence with a surprisingly strong punch. If a function is convex, then evaluating it after you average is never larger than averaging the evaluated values. In simples, f of ex is less than or equal to e of fx. Why? A convex curve bends upward. Draw 2 points on it, then connect them with a straight chord. The curve sits below that chord. Now pick a random input. Sometimes it lands on the left, sometimes on the right. The average input is the balance point. On the chord, the balance height is exactly the weighted average of the two endpoint heights. But because the curve lies underneath, the height at the balanced input is lower. That is Jensen. For many possible inputs, repeat the same idea. The center of mass of points on a convex graph must sit above the graph at the center of mass of the x values. A classic example is the square function. The square of the average is at most the average of the squares. That gap is variance. Jensen is why randomness can have a cost. For convex losses, fluctuations hurt more on bad days than they help on good days. Flip the bending, and concave functions reverse the inequality. That is why the log of an average is at least the average log. So the memory hook is simple. Convex curves punish mixing. Average first, then curve, gives the lower answer.